Okay. Talk about with regards to Linux file systems. Workstations over the years that have come in, but I get a kind of configuration everywhere. But it's just so seldom that but occasionally so, and there used to be quite a bit of file system B-tree format. It's identical in the structure for riser. Like single sector failure could cause the same problem as it does on Mac OS X. But because Hans Reiser, we call it the file system. Hans Reiser killed his wife and buried her on a trail in San Francisco, and so that seemed to hurt his file system quite a bit. I can't understand why, but he opened it up to the public, and so apparently other people have carried on the torch, but it's kind of disappeared. One of the reasons that you would have had the riser system was meant for smaller, older disks. And as we've increased disks, the update that it requires across all of the disks for all of the inode tables and block cylinder groups makes it really, really slow. And makes a really long time for you to check if there's a problem, and you have to run across all the tables. So ext4 came out. ext4 is to address some of the speed problems and the other content that happens. ext4 removes some redundancy. So there is redundancy across the entire disk. Using what's called magic numbers, there's many tables that are redundant all the way across the disk. So ext4 removed some of the metadata so that it didn't have to be updated as often, that there would be less locations, but the inode tables would still maintain a majority of what was necessary in order to keep it in case of a failure or a crash. So there's ext2, ext3, and ext4. ext2 and ext3 are fundamentally almost identical. The only thing that's different is journaling. You don't actually try to do a recovery to ext3, you just do ext2 because you don't need the journaling. Does that make sense? So all the tools basically just say, I support ext3, but it's really ext2, and they just turn off journaling. ext4, it's removing some of the metadata, so there are certain tables that you can only have content from one location, but the inode table still remains intact, and it's really still redundant, so you don't really lose files, but deleted files are really hard to recover. Deleted files still have to be carved, but there's not like a flag in the operating system like there is with NTFS, where there's just a flag and it's still a deleted file, but it still exists. Once the inode table is released, then the content is released, then you can only carve for it. And if you carve for it, you also have the pointer for indirection that will be in the way. And I'll show you what that looks like in a minute. So when you're looking at your Linux file systems, now, if it's an embedded device like a NAS box, most of all of the other folders are static. They don't change. Whoever made them, there's a configuration file that gets written, and that's usually written on flash or the disk somewhere. Most of them don't change at all. The only one is they usually have a shared folder or a home folder, and then that's shared to the public, and that's where you're writing your NAS content to. But if it was a real live system, a server or something like that, there's some files that somebody probably would want if you were looking at things. So as a whole, they almost always want their etc directory because that's all the custom and content and other things that they've done with the configuration and other items. Their var directory they would want. Unless they're a programmer, they probably don't care about their bin directory or any of the other stuff, but if they are a programmer, they're going to want their compiled content and some of the other stuff that exists. So most of the other stuff can be rebuilt, but those would be the ones that you'd want, is the etc directory and the var directory. Otherwise, it's the home directory that somebody's looking for. You don't really need the swap file for data recovery, for forensics maybe. So the rest of it is kind of irrelevant. The most part, it's going to be the home directory and the share directory as we're going through the process. So you're using everything in Linux is a file. A file is a file is a file. The directory structure is a file. The problem with this is that even though like Mac OS X is the same thing, a file is a file is a file, including directory structure, all the other systems seem to know how to parse the file structure and the catalog structure to actually represent the directory structure correctly, whereas a lot of times in Linux utilities, that's not the case. That the tool that you're using doesn't enumerate the data from the text file that is your catalog for your directory. Does that make sense? So sometimes you just get the file back that says what the directory structure was, but that's not the directory. So you have to go follow that through. A lot of tools will mount it and then follow it through, other ones won't. So physically, what we're actually looking at, I've actually asked this 100,000 times. Almost nobody ever modifies any of the journaling functions. The basic journaling seems to be left in place. ext2 and 3's file layout looks a lot like this. Like, you know, fundamentally, you are dealing with a layout of block groups, and then they are repeated across the drive. Your directory entries are actually text files or files that contain the pointers to the data as you continue on, and it looks like this. So you have your MBR, you have your partition structures, you still have MBRs, you still have these in all of the other disks as well, same as usual, and you're still looking for the same flags. And then inside your partition structure, you have cylinder groups, and then inside of that, you actually have an inode table that will keep track of the content as it's moving around on the disk. And those are the things that have to be updated, and they have to be updated frequently. Every time you touch something, a date and time has to get updated in all of them, so the disk will eventually crawl all the way through it, making all of those updates. Now, when you're trying to look at files and you're looking at folders, this is where things kind of get a little bit scary, I guess. It really has to do with the 12 blocks, 12 direct blocks before the indirect. So it looks like this. So you have a group of data that will be contiguous before it points to an indirect pointer, and then the other 12 blocks of data, and so on and so on. So when you carve data, it has a distinct look to it. And one of the things that I want to point out, find one. See if I can locate one really quick. I know I have it. Half a second, because I want you to see. Well, I'll have to carve one. I'll have to go and get one. Here we go. All right, so when you carve a picture in Linux from ext, and your tool does not, it's not a Linux tool, so you're not running in Linux, so it doesn't know how to deal with this. So this is out of RStudio. RStudio carves a picture, and it looks like this. Now, a lot of people who have done RAID array work think that this looks like a problem that is exhibited by a slice size in a RAID array. Do you understand what I mean? But this isn't. This isn't a slice size problem in a RAID array, so you need to get used to seeing this. If this was a slice problem in a RAID array, you would actually see a far worse problem than this. There would be a bigger shift, it would be in a smaller chunk, and then there would be a repeating chunk, and then it would not show the rest of the picture. There would be something that would be corrupt, or something would not look right. So in this case, what you have is this blemish that is basically extra data that is throwing off the algorithm. And this, to me, looks okay. My mind immediately interprets this as okay. Was this okay to give to the client? No. Is this okay for me to know that my drive and my data is correct before I have to go an extra step and say, let's go carve it in X-Ways Forensics, or let's go use Foremost or a forensics tool that knows about indirect blocks and direct blocks and carves it out correctly. So those are the other steps. So if you're dealing with a RAID array, this is initially what you're going to be looking at, because none of your tools, or at least the manual tool that we're going to use, which is RStudio, is going to show it like this. It's not going to be chopped up. I'll show you some RAID array pictures in a minute, but that's the thing I need you to realize. You know what I mean by this? This is not a screwed up picture. This is correct. I don't know if I have any other way of looking at content. Let's see if any others are messed up in that way. I'll probably have to go, if I wanted more, I'll have to go find some or figure them out. These are some tests that I did. But just understand that is correct. It throws off the algorithm and it's fine, but you don't pay attention to color and those kind of things. And we'll see this a couple of times as we're going through this process. Okay? So just understand that's what we're talking about, is these pointers and the tools that actually display the pointer. Once you process the catalog correctly, if you can process the inode table and you can get that far, and you can right click and say show files, it'll do exactly the same thing MFT entries do. It'll get rid of fragmentation, it'll get rid of all of the problems, and it'll lay the data out correctly. So if I got this far, I can probably get the file system to work. Okay? All right. Everybody understand? The other thing too, just like I said earlier, you may also have extreme luck if you're using different distributions. And so I do use different distributions all the time. And I have a huge amount of success with Knoppix. Knoppix has a huge amount of drivers and other tools inside of it that are, it's been around for a really long time. It's a live boot CD, and it has a lot of the drivers and functionality, and it has a huge amount of RAID array controllers in it. So if I'm working on an old RAID server or something like that, starting something up in Knoppix and looking at it might actually be a great choice. And so I do typically save all those disks that you will actually get. So we're gonna take a look at this, but we're really gonna do this as a RAID array. I want to function based on this in RAID array because I'm going to teach you the NAS box stuff in the RAID array content altogether. Okay, so let's talk about RAID content first, and then we're going to come back and talk about the variations. One of the biggest variations I see all the time is called XFS. What page are we on, by the way?
160.
What is it?
160.
160. So, when we're dealing with RAID arrays, we have functionally at least the ordinary and the normal RAID arrays that we will deal with, which is going to be RAID 0 and RAID 5. RAID 1 is a mirror. If you hear RAID 1, you're still going to treat it as whatever the other option is, because sometimes RAID 1 also involves RAID 5 that then is mirrored and things like that. You have half of your disks are fine. They still work fine. You can still go do your recovery on half of the disk. You don't need to worry about RAID 1. So you don't need an option that says, oh, this is a RAID 1. So now when you're dealing with this and the possible options, you have LVMs and XFS and certain other items that are going to be Linux-based or embedded arrays. And if you have any of those things, like a Buffalo Terra station, you can't easily manually do XFS. You need a tool that does XFS. So if it's a Buffalo Terra station, and you can find out these things usually fairly easily and quickly just by looking up on Google real quick, what does this support? But the majority of them, a good 90% of the RAID arrays out there are going to be simple, straightforward RAID 0 and RAID 5 arrays. And that's built into so many things that by default, almost always I can try something and get an answer in a few minutes. And then you can recognize whether or not, if it's Linux or if it's an LVM or something else. There are cheap and easy tools to do LVMs and to do that. Now the other thing is the hard ones. The arrays that are not cheap and that are not easy. Those are the IBM RAID arrays, the compact HP RAID arrays. Those are going to be variations of delayed parity and JFFS and a couple of other versions of those kind of things. Now, here's the weird thing about those RAID arrays. They have a configuration file on disks. You don't need it. You don't need to know it. You will have automatic tools in every single situation that can solve that problem. Okay? So if you hear compact RAID array, HP RAID array, IBM RAID array, look at the controller and look at what's possible, and you will be able to figure it out fairly quickly because there's only a handful of options. You'd be surprised at some of the RAID arrays, like an IBM RAID array, only has 4 possible segments. So you cannot choose 1 meg slice size. You can't do things like that with some of the controllers. They will limit you as to their capabilities. So you have to be, once you read what the controller does, and if somebody is high-end enough that they have a Compaq or an IBM or any of those things, then it's not just going to be your run-of-the-mill mystery box that you're going to get in the mail. Okay? Everybody understand what I mean by this? So I'm going to go through those two, and I'll answer those questions at the end. But I will tell you that this is one of the other things. I'll show you real quick. Let's see. So this is X-Ways Forensics. So if you buy X-Ways Forensics, it'll already have a subset of the choices that are already done for you, already laid out. And believe it or not, this is almost all that there is. There's only really 3 variations. There's some things that just don't exist in any other variation. And I'm going to show you this because by process of elimination, you can figure out any RAID array and its possibilities. And even though it looks like there's 72 combinations and all this other bullcrap, it really turns out there's only going to be like 6 or 10. And that's it. And then you're done. So when you're looking at this, see on RAID 5, when you're dealing with these, you have basically 3 manufacturers. You have 3 basic manufacturers, and those are the ones you deal with. Now, HP has a delayed parity, and the storage for the container is on the disk. And for a cheap tool to a free tool, you can figure that out without having to do the work because it's an extra delayed parity, and there will be some items when you select it because there's 16, 32, 4, 16, 32, I think are the numbers. Those are the primary numbers you use for delayed parity. So you can figure those things out, but you don't need to worry about it. And then, at least when you're getting into these categories, you won't be able to manually look at pictures or content to figure this out. But the configuration is on the disk. And you can get the configuration and you can get the answer to it. Okay? And you'll make a lot of money because they will be expensive. And then 6, you can support directly inside of RStudios. All right, so let's talk about RAID. And then we'll probably split this up. We'll do this part tonight. We'll do all the labs in the morning. Everybody good with that? That way everybody's not completely burned out when we're trying to do RAID array. All right, because it's fun and it's neat, but you need a clear mind. So RAID, some RAID arrays are not redundant. That's one of the problems. Now, when you're talking about RAID, you're talking a redundant array of inexpensive or independent drives, devices. I've heard both comments. I've heard it said both ways. I've seen it in documentation both ways. And I think it started out as inexpensive, but somebody's boss said, where's the inexpensive part? Because it almost always started out with SCSI drives, SCSI arrays, high-end ones, because you had to have a controller that could do math. There was a lot involved with it. And so some of the arrays are not redundant, and we're going to talk about those in a minute. And then different ones have a different number of drives that are necessary for that to occur. So let's talk about the ones that are not RAID arrays right off the bat. JBOD. Sounds really cool. It means just a bunch of disks. And usually they're concatenated together in some way. So they're not striped. There's no real intelligence. There's no redundancy. It's just one drive added to the other drive, added to the other drive. But this doesn't mean anything specific. You don't know what you have most of the time, except that they are usually in sequential order. And most of the time it's 2 drives. It's not going to be anything really substantial because once you get past that, you're in high risk category. You're still in high risk category with just the 2. So JBOD, almost always all you're doing is concatenating 2 disks together. It's extremely easy to do. You can do it in almost any piece of software. You can even do it at a DOS prompt. If you image 2 images in DD, as long as you've got the same number of sectors and the right number of sectors, you can do a copy/B, and you can add one file to the other, and then actually make an image file and then process it as normal. But you can always add them. We'll talk about those shortly in a minute. So usually what you're looking at is inside of a box like a LaCie. Now, LaCie disks We have a running joke about those. It's a let's see if we can get your data back, because these things were trash and they were terrible and they would burn your disks. Their power supplies would burn out all the time. And they almost always never had a fan in them to cool their drives off. They wanted to be silent and look cool. Usually designed by Porsche. Yeah, right. Pretty bad design. So you open the drives and it looks like this. Now, what would usually be in here is something like this. It would be a 500 gig and a 500 gig, and then they'd be connected across a cable, and this board is doing all the work. Whatever's happening, whether or not it be a RAID array, whether or not it be a JBOD, whether or not it be, some just, dumb thing that you don't expect, it's these boards. And for a while we collected these boards because, sometimes you didn't know what was going on. You didn't know what was going to happen. You won't see these now normally because LaCie got bought and they just kind of disappeared off the shelf. Mainly because somebody's using them because of their OEM process now. So a lot of times you would open this up, it would be really hot, it would melt the cable, there would be all kinds of problems. But let's assume that the disks that are in there, there's something wrong with the disk, you image it, and you come back after you've imaged it on the Atola, the DeepSpar, the PC3000. Now, what are you looking at as far as the drives go? Sometimes what would happen is one of the drives would die. So let's look at it from this example. Let's say this is drive 0 and this is drive 1. Let's say drive 0 is the first one in the array. How will you know that it's the first one? Whether it's JBOD, array, it doesn't make any difference. How do you know if it's the first one? The partition table will be there. Your MBR will be on the first disk. Always. In this case, your partition table will always be on the first one, because these are going to be concatenated together. If it's RAID 0, which we'll get into what that means in a minute, if it's RAID 0, you still have the beginning of the drive and then slices that are going to be distributed amongst it. Which one's disk 1? The one with your partition table on it. And almost always the same scenario again with RAID 5. If we had 3 drives in the array, which is not going to fit in here, then we have the same thing. We have a partition that's going to exist, a partition table that's going to exist as the first disk. So I can't fool you into believing what the first disk is. You already know, as soon as we mount it in a system, you can go look at 55AA and know which one it is. Right? Everybody good with that? On the first disk, let's say the first disk dies. So you plug in one drive and it's completely dead. You open it up and it's platter dust. It's completely dust inside. So the second disk is the one that survives. What do you have? What can you do? What can you recover? You carve. You can carve files from the second drive because there is no catalog. You have no catalog at all, right? So, you can say that again?
You can't boot from the second drive, right?
No, but these don't really boot. Most of the time these don't boot. These are mostly external devices, especially if it's a JBOD. The closest thing that comes to this board is in control of it. You could have some that boot, like the next one. That one boots. But this one wouldn't boot. This one also, like let's say the second drive dies, everything's on the first drive. So you have a catalog and you have everything, but as you're reading the disk, at some point in time, the catalog points to content that's on the second disk. And when you get there, there is no second disk. So it's completely dead. So it's going to point to LBA blocks that exist on the second one. Here's another really unique thing that happens. In a lot of cases, these have an HPA on them, twice the size of their drive. So you'll plug it in, and it will say on the label, I'm a 500 gig drive. But the HPA on the drive when you plug it in says I'm 1 terabyte. There's an HPA that is set to twice the size of the drive so that the drive can think it has all these other sectors. This board's job is to renumber the LBA blocks on the second drive. That's all it does. It just adds the content of the first one to the content of the second one. So your catalog still will work up to 2 terabytes. It'll still look at it and be fine. It'll just be on the second drive. Does that make sense? Very simple, very easy to deal with. Now your hope is you save both of those drives. Then you can actually, like I said, just copy them together. But you have to have the same number of sectors, because if you're off by one sector, it throws off all of your clusters. Remember, things are grouped in groups of 8. So it'll throw off your clusters. So you have to make sure you have an equal number of sectors on each one, and that if you're missing some sectors that you start in the right location. Or you can use RStudio, you can do volume set and you can add them together. So it just adds them together logically. Okay? Everybody okay with this so far? It's pretty stupid, pretty straightforward, or you can copy, you can recover just from each independent drive. Usually these drives, like, because these were called LaCie big disks and stuff like that, most of the time these were dropped. And one of the drives is destroyed. That's usually what happens. One of them's powdered. And you hope it's the second one, because that has less data on it most of the time also. Because they fill up in order. The LBA blocks from here to here. So it may overlap. There may be some data on the second disk, but your catalog and all your content on the first disk is the most important. NAS boxes. So this is a LaCie NAS box. So this LaCie NAS box plugs in. It has, in this particular instance, you'll have an Ethernet port, and that's the control mechanism. On the drive itself, this is what you're looking at. You know what this is? Anybody know what that is? What do you think it is? It's a board. Yeah, it's a board. And what's on this board? What do you think it might be? If it's a LaCie NAS box, it will be a Linux embedded. This is it. There's a motherboard, a processor, memory. Linux is embedded on here and runs on this device. And that's all the control mechanism, everything else. All it does is share out a folder that is the combined of this drive. Now, this is a RAID 0. These were striped. So content from this disk is striped with this disk. They are not concatenated, they're striped. So we'll talk about RAID 0 in a minute. But this drive, this boots and then shares out that drive. So now here's the thing. On this particular drive, you'll see I have a label that says Nix Terra. This is a 500 gig drive. This was a 500 gig drive, but it was damaged. So I imaged it. In this case, I imaged it on a deep spar. This is 97, 98, 2007, 2008. I imaged it on the deep spar to a terabyte hard drive. I didn't have a config drive. It couldn't do it back then. It's one of the reasons I asked for it. But I imaged it, and then I set the HPA on this drive equal to 500, which I was surprised actually works, because a lot of times Linux did not honor HPAs. So in this particular instance, I made it a 500 gig, and that's 500 gig. If it was still a terabyte, then these two would not match up and there would be an overlap. They have to be equal in size for you to stripe them correctly. So I took a terabyte, I made it a 500 gig, I put it back in the system, and I mounted it. Now I didn't have to do this. I could do this. I could use, in Linux, I could use MD80M and I could redo the drives from there, or I could do it in RStudios. I can do RAID 0 in a number of different ways. I don't need any of this to do it. Okay? But in this particular instance, sometimes it's easier just to throw the box right in the back of the box, plug it back in, and let's do a recovery. So I did image it. I recovered everything but like 16 sectors. And then I brought it back up, plugged it back in, and went to work. And I'm surprised, but remember, you have to set an HPA. They have to be equal. Otherwise, I would have had to find another drive, copy the partition, re-image it, and make it equal to it, and find a drive with the same number of sectors. Or I could have just done it in software. I don't even try to do it in boxes anymore. I just go ahead and do it in software. I don't even bother anymore doing any of this. I just immediately plug it in and try to do it directly in software. Okay, everybody good with that? All right. And then you have dynamic disks. Now, dynamic disks are actually really easy. Dynamic disks, if you plug them into RStudio, RStudio will tell you, it will read the configuration file, and it will immediately tell you which disks you're missing. So, and it will do them automatically. If you just save them all and plug them in, it'll figure them out automatically. So dynamic disks have a configuration that's written on them. Windows keeps track of those dynamic disks, and when you add them back into RStudio, it will assemble them on its own. All you have to do is fix the disks and get them back up and running. So that's all you have to do, if you can do that. Otherwise, each independent disk is storing data, and you have the same situation you have with concatenated disks. You can carve some, and you can get some out with the catalog. But that's still as good as it gets. So you're still carving and trying to get those back together. Those are not RAID per se. So those are just dynamic disks. So RAID, when we're talking about RAID, these are the primary things we're dealing with almost always. RAID 0, RAID 1, RAID 5. We don't have to do a recovery in RAID 1 almost ever, because if it was RAID 1, there's another disk. Half of the array is good. So RAID 0 is striped. There's a chunk on each drive. RAID 1 is a mirror. So if you have a 500 gig and a 500 gig in RAID 0, you can make it 1 terabyte by slicing it across the drives. If you have a mirror and it's a 500 gig and a 500 gig, you only have 500 gigs of space. Everything you write to it then will be written to the second drive. Now the controllers fail all the time. And when they fail, one of the drives just gets abandoned. And when that happens, you can still recover from that drive even if it's the first drive that dies, but now they may be out of sync and it may be earlier in the day, basically. Does that make sense? So it may have been 6 months ago. You don't know when it fell off the array, so they may not have current data on it when the other drive dies in a mirror. And this does not have to be the configuration. You could have a RAID 5 array and mirror it. You can still have RAID 0 and mirror it. You just have to have twice as many drives. So you separate them out and you say these two go here and these two go here, and I can work on them. Now, in RAID 0, what's the minimum number of drives? 2. What's the maximum number of drives?
Can have as many as you want.
Yep, you can have as many as you want, as many as your system will let you add. Isn't that asinine? It will let you keep adding and adding. I have seen a RAID 0 array with 45 drives in a RAID 0 array. And every time you add one, that just increases your chances of failure, because all you have to do is lose one. If you lose one, unless you can recover it or do something, you might not get lucky enough to get any data back from it. There's going to always be a chunk missing if it's big enough to span all the drives. So if it is a chunk that is missing from, say, a PST file or an EDB database or something else, it's actually going to just fall apart. So when you mirror, again, all you're doing is duplicating your drives. Whatever the situation is, you're going to mirror it, then you're going to duplicate your drives. So now in RAID 5 and RAID 6, what we're going to be dealing with is this. RAID 5, what's the minimum number of drives? 3. What's your maximum number of drives? It's whatever you can keep plugging in and however you can keep getting them up. So however many your RAID controller can have. And there's ways to keep adding to those and expanding RAID controllers. Again, 45. I have recovered from RAID 0 arrays with 14 disks in RAID 0 arrays on a common basis as well. So people are crazy with some of this stuff. We're going to talk about these in a minute, and I'm going to explain them. And then RAID 6 was meant to add additional redundancy to RAID 5 because RAID 5 has actually become fairly unstable because the drives are crappy. So you have one drive die in your array. You can have X minus 1. So however many drives you have, minus 1, your array will live. But it will be in a degraded state and a degraded state. And that degraded state is not going to be as fast as it normally would be in any other circumstance. And then RAID 6, you can have 2 drives die before you're in a degraded state, and that it's degraded right away, but it won't put it in danger. You can still have 2 drives die and you can survive. So here's the story with RAID 0. RAID 0 was designed for speed. RAID 0 was supposed to be, I'm a video person and I needed to be able to use 2 heads to scrub a disk at the same time, so I'm working on audio, video, other content. Now, you have to forgive me for saying this. I don't think RAID 0 should be called RAID at all. There's no redundancy, and it's a marketing thing that fools everybody. You're in the store, you see a drive, it says RAID 0. I've got 4 drives in my RAID 0 array, such as an AS400 as an example. An AS400 has 4 drives in a RAID 0. That's how an AS400, a very valuable, very needed, now it is running on SCSI drives, so at least it is pretty redundant and pretty robust, but you don't have any redundancy, and I think we should get rid of it, and I think what we should call it instead is AIDS. It's an array of inexpensive disks that suck. If you don't have redundancy and you have multiple drives, you are just asking for problems. So as soon as you make a file, you should copy it off. That's the way it should go. Copy it off just as fast as you can. So there are a lot of arrays, like for instance, SGI systems had a long list of drives as they were, because SGI systems were primarily used for video production systems and things like that. And so they would be making a movie and they would render content, they would be sitting on these arrays, and one drive in the array would die, and a chunk of the movie and a chunk of the video would be gone, and Babylon 5 would be over, and there would be no more piece of Babylon 5. So that's the kind of thing that happened. Just pointing that out. So it's an array of inexpensive disks that suck. So it is there for speed, and that's primarily it. Don't put anything. In my opinion, solid state is not much better. That's my opinion, but we'll have some arguments about that. So RAID, now here's the most common thing I see in RAID 0. In RAID 0, pay no attention to the man in the back. That's Scott Lalis. So, hey Scott, how are you?
Hello, Scott.
I've been talking about you all week.
Well, with AIDS.
Yes, right now. So, in this particular instance, RAID 0, the most common I see is I see 2 drives or I see 4 drives. I almost don't see very large or other arrays, not that I don't. It happens from time to time, especially with Mac people, because Mac people can do a software RAID array and they can just keep plugging stuff in and keep making arrays. But the majority of them are going to be 2 disks or 4 disks. I don't normally see like an odd number like 3. If I saw 3, I'd probably think it's RAID 5 right away, but it does happen here and there, but for the most part, it's a controller with 2 or 4, and not a lot more. And then some of them that can be reconfigurable, like a Buffalo RAID array, Buffalo Terror Station can be reconfigured with their 4 drives can become RAID 5. So here's the thing, is you almost always know, no matter what I say here with 4 drives, so somebody sends me a mystery box, the thing is, they don't always number them. Like they pull them out of an array, especially people at home who have, they just pull them out and they put them in a box and they, throw a piece of paper in and say, here Scott, fix this, and ship it off to you. And so you have 4 mystery drives that come in the RAID array and you have to figure it out. Or, as we had the other day, we had the CEO of the company that came over and deleted the configuration file on his RAID array for some unknown reason, have no idea. And then you have to log in remotely and try to figure it out because they don't know what it is for real. Okay, so you don't really have 72 possible combinations. For example, right away, which one's the first drive? MBR. So then you only have to figure out the other 3, right? So, and you could just do it trial and error fairly quickly and figure out which ones are the segments and what they are. Now, again, not every controller, especially cheap controllers, have very limited options. If somebody tells you you have a high point controller and that's your cheap option, or you have a 3-wire controller, which might be $300 or $400, you go and you look at the specs and you'll find out you can't do a 2K or a 4K or an 8K block. You can only do a 32, a 64, a 128, and a 256, and not always 256. LaCie drives will do 256 sometimes on you. I'm just going to tell you that. So sometimes it's 256, sometimes it's 512. But you can have a chunk that actually changes. So you only have 3 possible segment sizes and then 3 possible orders. So at most you have 9 possible choices because you already know which one's disk 1. Now you could figure out, there are mathematical ways. You can open up the drive in a hex editor. You can go look at 64K and you can look for a buffer, a little blank space in between 2 segments because they're going to start in the slice sizes just like they do with sectors at 512 byte boundary. You can go look at them if you want. You can figure them out. A lot of people have written data on that, and if you want to do that, you can go read it and figure it out. I have a different way of doing it more quickly, and that's why I say, and a lot of times, in a few minutes, I can figure it out. So I'm going to break things down into their segments, and I'm going to try it. Now, you do have to take a little bit of this with a grain of salt because you do have to look at an enormous amount of data. You have to look at like 200 pictures in order to get a good view. If they're all right, you're right. But if you're not all right, to get a good idea of them, you have to get... So you have items that will bridge the gap. Sometimes they will sit on both sides and it will look fine. Or they have compression, or they're smaller, and they will look okay. But if you open up a 2 meg picture and the 2 meg picture isn't right, you're not right. But you can probably tell what's right or wrong looking at a 2 meg picture. I can do it at glance now. I can almost always tell right away. So you have an MBR on the first disk. So you put the first disk in that position. Then you have to break down each one of the others. Now, I will also tell you there's automatic ways to do this now. I've been doing this long before there was automatic ways. There was not, RAID Reconstructor was one of the first tools, and when it would fail, you had no other choice. So about 2010 or so, they started coming out with automatic ways of doing this, and there is a free solution called Reclaim Me, a free solution called Reclaim Me, which is actually pretty good. Actually does a really good job at looking at this. But I'm going to do it manually and teach you how it looks, and then you can actually go back and figure it out later. And I'm going to do it with pictures, because almost every single device has a picture of some kind on it. So what I'm going to do is I'm going to look in between segment sizes. I'm going to look at pictures. I'm going to start with big pictures, and then I'm going to look at anything that's over 1K or 512, and then so on and so on through each one of these segments. So a 2 meg picture is going to fall outside this range. Then I'm going to look at a 128K picture, or something between 128 and 256K, and try to figure it out. The other thing is, too, your MFT record is going to be wrong if you're wrong. So your size is sometimes an implication of what your messed up MFT record is. But you can figure it out really quickly. So let me show you how I do things like this. Like this. What is wrong? And I asked this in one class. I asked this in one class, and a guy in the back row, I said, what is wrong with this? And the guy in the back row goes, nothing. Sorry. That wasn't me. I didn't do it. Nothing. Anyway, so what is wrong? What is wrong with this? What is wrong with all you guys? I can't believe you thought that was funny. No. What is wrong with this? Anybody have any idea?
Orso's missing.
I'm missing a slice. There is a slice missing. And this particular instance, I'm doing a recovery. I only have one drive. Somebody mailed in one drive, and I'm working on it. And then I get it. I actually fix the drive, and I start getting the data back. And I look at it, and I'm like, holy Toledo, something is missing here. So I call the guy, and he goes, yeah, I know you charge by the drive, so I only sent you the one that was broke. That's how that happened. So in a situation like this, where you're missing, hang on a second. This is where my Mac finally had messed up on an image. That is weird. So there actually is another picture, and for some reason it is not displayed. Give me 10 seconds and I'll switch. These new Macs. Because in the book has the rest of the picture, doesn't it? First time ever. Okay. All right, here it is. That is really weird. All right, so in this particular picture, so this would have been something like a RAID 5 where there would have been something that would have been out of place in one of the slices. So one of the drives would be out of order in this because these two things exist. This is a real thing. This is a Windows, these are two Windows pictures that exist. And so they're in a slice that's out of order. So the beginning is correct, then it's showing the next piece from the next slice and then comes back to the next piece. So these are drives that are out of order where I would have to try to figure out what that order is. So that would be one of the things you could tell right away. And you could probably even tell what the slice size is. If you look at the picture and I told you it's 140K, what do you think that slice size would be? It actually works exactly the same as you would think. You're folding a piece of paper or you're doing something. So if it's 140K, and yeah, so if you divide it by 2 approximately, and you know your segment sizes can only be in chunks of 32K, 64, 32, 64, 128, 256. So in this particular instance, that slice would probably be 64, right? So if we're at 140, subtract off the difference between 64 and 128. That would be a little bit of the difference, and then there would be divide by 2, and that would be a 64K slice. So you can start seeing things like this as you're going through the process, and you've done it a few times. Stick people, that's really small, so these are going to be small images that are going to be intact. Then you actually have things like this are a thumbnail. Like this is a thumbnail that came out of another picture. And so this piece was intact. It's a small picture that's intact, so it's not sitting on the border of a slice or anything along those lines. But this is the real picture. This is the bigger picture that actually did exist. And so the thumbnail for this picture was intact, but this picture is not intact. So you can actually tell this was the clouds, this is the content, here's the color. This one gets thrown off. Ignore color though. Color, because in any segment where there's something wrong in a JPEG algorithm, it throws it off. And so it's slightly out of bounds from that standpoint. So if you look though, you'll start to see something like this, like all the way across the top. Does this look correct? If these are drives and they're in order, their slices are going to be in order of their segment sizes. Okay? So if you can think of this like a picture, like I've got a big picture, a 2 meg picture. If you chop it up, here's one piece, drive 0. Then here's drive 1. Then here's drive 2. Those segments will start to look weird because they'll start to look in order, and you'll start to see these segments that go across like this, and then it will loop over and it will start looking like a mess. And I'm going to show you a picture in a minute in a RAID 5 of what this looks like. And you can see here even this slice size going across the top is fine, but then all of a sudden there's a segment that's wrong and you have another picture that's thrown off of there. And a lot of this has to do with the orientation of the order of the layout of the drives and which choice you make for the layout of the blocks. Whether or not it's left synchronous, left asynchronous. I'll show you these things in a minute and what they mean. And then you actually have like when you have files and you have content that's completely out of bounds and you're missing a drive or you're missing content, you'll start to see things like this. But the drives are in order because this is a huge raw file. And if you look, the segment for what's in order is actually correct. Because if this is one drive, then this is the other drive. And it's exactly like these puzzle pieces that you would get. Remember those puzzles as kids that would have a picture on it and there'd be these little squares and you have to move them around? That's exactly what this looks like. That's exactly what a drive looks like. And then when you finally get it, it looks right. It looks like this. So I'm gonna play a sound file for you that came off of a RAID array. And hopefully it'll be loud enough. There we go. All right, I'm going to play a sound file. So as you make it through the slices and it's rotating through it, as long as the codec is similar, the same, you've got something very similar that it can process, it'll play right through. It'll do it on videos, it'll do it on pictures, it'll do it on a number of things, and you'll just get a mix mash of the stuff together. And so and literally you can hear it. It'll actually just physically sound that way. All right. So we're going to do the RAID lab in the morning, and we'll do RAID 0 and RAID 5 first thing in the morning, because you'll be amazed at how quick RAID 0 will go. RAID 0 is actually the least complicated of anything. It ends up happening in a minute. Once you've done RAID 5, it looks so easy. So RAID 5. So here's the thing. RAID 5 was designed around the theory that you needed robustness, something that's going to be redundant. Well, a lot of the ones that are in between RAID 0, RAID 1, and RAID 5, we just don't see anymore. They're obsolete. They don't have a lot of place where somebody spent some money or time putting them into a controller. So a lot of the low-end controllers and things these days will only do some very simple stuff, RAID 0, RAID 1, RAID 5, JBOD. So in this particular case, it does this by storing what's called parity, and it distributes the parity across all the drives. And there's a controller that's necessary to accomplish this math in a fast way. So the controller itself, in many cases, you have two types of controllers. You have a discrete controller and you have a host-based controller. The host-based controller uses your processor. So it's a cheap controller, like a high-point controller or something like that, that will use your controller, your processor, for processing power instead of having a processor on it, versus a RISC processor or something that might be on a board. So you can tell by price most of the time. A $300 controller and higher has probably got its own processor. It has speed. You can see it on there to say how many megahertz it is. And then on a low-end one, it'll be a $100 controller or whatever's built in on the motherboard. It's going to use your CPU for its processing power. Now, the more drives you add to your RAID array, if a drive dies, it's going to suck more power off of your processor. So you're going to feel it a lot more severely than you will if it's on its own controller in a discrete controller like this. And what we're going to do when we're reassembling all of this stuff is do this in software. We're not going to be reattaching it to the hardware. We're not going to be, very seldom do I reattach it to the hardware. Almost always I'm doing it right straight away in software. It's a lot easier, and I have a lot better solutions. So that physically at least is what we're going to try to do. Now let me show you. I'm not going to try to use these Wikipedia things. At the time I had to make an animation for how RAID works. And so here is my RAID animation. Today, just not my day. All right, so here's my RAID animation. Now here's the story. You have, whenever you have a drive and it's broken up into the segment, so it's a 64K segment. So here we have a slice that's 64K, 64K, 64K. Then it would produce using an exclusive OR routine. So it would do a mathematical equation called exclusive OR and produce a new 64K segment, a new 64K slice that has parity in it, so you can reverse the process. And so anytime that you're looking at it, you can figure out what you're missing if you know what your parity is. So you can have one drive die, and you always have it. So no matter what you do, if you throw an X on any one of these, you have enough material to rebuild the algorithm. So this is what it looks like. Now, I used to use this for sales as to why a company needs to have a RAID array, and I didn't want to try to explain exclusive OR, because that's a little more difficult. So everybody who took financial classes or anything knows A plus B equals C, and they know they can figure it out. If you know what any one of those other two items are, you can figure out what the last one is. So that's what happens here. Now, and also, making it worse than possible, it may be possible for you to recover the one drive that fails in the RAID array, and you probably actually have two drives that fail in the RAID array instead of one, or you probably aren't seeing it. But I do sometimes get RAID arrays in that only one drive failed in a RAID 5 array, and I can still reassemble it from the existing drives. It does happen, But most of the time, something else has occurred. They can't get it to boot. Something else fell offline. And sometimes they force it online. That's another problem. So in this particular instance, if you look, no matter which drive went bad, the parity is rotated through all of the drives. Now it's technically diagonal in the parity. And so my analogy here is that it's just the containers on the bottom. But this is fundamentally how it works. Now if you have two drives that die, let's say number 2 dies also. And so you have 2 drives that have come in that are failed and 2 drives that are good. And you've received these drives and you've got to figure this out, fix them first, and then reassemble the RAID array. So you've got to do that part first. You still got to do all the manual stuff. Then you've got to turn around and do the logical reassembly. 2 drives died. Which one are you going to put back together? You're going to pick one, right? Because if you only need a RAID array and you can do X minus 1, you can reassemble the drives if you only have 3 of them. So are you going to fix both of them? You're going to try not to, right? So, 2 drives die. Which one do you need to pick?
The one that died last.
The one that died last. Because the one that died first, even if it was 24 hours ago, is now out of sync. Even if it was 15 minutes ago, it starts to fall out of sync. It's not as bad if it was only 15 minutes ago. But if it's 6 months ago, that dude's got old data on it that's not even going to come in alignment with the current one. Now, the problem is, what happens is, in an environment where there's a small business, most of the time this is a small business. This isn't going to be like at Ford or someplace like that. If you have a small business and there's 4 drives in an array, and the alarm goes off, the IT guy comes in and shuts it off because the manager is pissed off that he can't make a phone call without this siren in his ear, because it'll have an alarm. It'll go, rah, rah, rah. You'll turn it off, and then the urgency is gone, right? So then you say, hey, we need a new drive, and it's $600. And he goes, that's not in the budget. And then that guy says, screw this, I'm out of here. And he leaves or gets fired, whichever way that happens. And 6 months later, the other drive dies. How do you know which one died first? That guy's gone. The guy who probably knew is gone. Even if he stayed around when the second drive died, he got fired, right? The server's down, he gets fired. There's always something like that happens. Like, why didn't you warn us? Oh, I put a PO on your desk. What? Why didn't you tell me it was urgent? I did tell you it was urgent. Now it's your fault. So you have 2 drives that died. You don't really know unless you have a logging server somewhere that can tell you which one failed first. You don't know unless somebody knew which one went out first. They have to tell you, because the logging for the drives is on the array. And maybe you can figure it out by getting to it or looking for dates. So the other alternative you have is to look at a hex editor, go to MFT entries, and parse MFT entries like we were looking at earlier today. So take the MFT entries and spit them out and go look at them and see which drives have what date on them. Because if that one died 6 months ago, it won't have tomorrow's date or yesterday's date on it. None of them are going to have tomorrow's date on it. That's really unique when they do. It's like, oh my God, he's back from the future. So it will have, it'll stop at a certain point, and you don't know, maybe it'll be yesterday, maybe it'll be 6 months ago. You can look at MFT entries, parse them, or spit out the MFT entries that you have. You can use the same method I showed you earlier, where we use like a quick scan, parse them out, spit out $MFT, even from individual drives one at a time. It finds individual file records. Spit them out, and then use something like MFT Ripper or something to actually spit out a spreadsheet, see which ones have the newest date. Look at files, see which ones have the newest date. JPEGs, in a lot of cases, will have EXIF information in them. And if you're lucky enough that they were current pictures, you'll know which ones were the newer pictures. Those are the only other things I can think of that will tell you this. Otherwise, go look at log files. You can go figure out in log files or the system event files if you can get them off of a drive. Your problem is it's fragmented across all the drives, and maybe the chunk you need is on one of these drives. So your only other option is pick one. Pick one and repair it, and then try to reassemble it. And you'll know if you're wrong because you can't get any of your options to work. And you'll only have 6 to 10 possible options. I'll explain those as we go through them. Tomorrow it'll be 6 or 10. But in this particular realm, that's what you're dealing with, is pick one, fix it. If you fix it and it's not the right one, then you got to fix the other one. Right? Because 2 drives won't give you any data back. And 1 drive that's the old drive isn't going to give you current data. That's going to be a problem. So you've got to fix the one that died last. Everybody understand? Now, this is the other thing people do all the time that's really bad. They image the 2 good drives. Now, the only reason you image the 2 good drives is if you're going to use those for parts. You don't need to image them right now because you will spend hours imaging 2 drives and you haven't fixed these 2. So unless you're going to steal parts from them, there's no reason to image those right now and waste the time. You need to fix these 2. If you cannot fix